Hello there, ROS developers, and welcome to this live class number 114, where we are going to see some examples of reinforcement learning. Specifically, we are going to see some examples of dynamic programming. So, let's go for it. Hello there, ROS developers. How are you? Welcome everybody to this new live class number 114, where, as I have just said, we are going to be talking a little bit about reinforcement learning, specifically about dynamic programming, which we are going to see right now what it is. So yeah, welcome everybody. And let me have a quick look at the chat and let me know, please, in the chat also if everything is fine, if sound is fine, image is fine, if everything is working correctly. I can see many people here in the chat. Hello everybody, hello from Colombia. Hello, sorry for being late, says Engineering Nation, no problem. Hi, it is okay, fine. Okay, excellent. Hello from Germany also. Great, so welcome everybody. So let's not lose any more time and let's go for it. So probably we have some new people here in the live class. Some of you already, I know you from the names, but for the new people, let me just explain you that this is not a normal live class, let's say, because we like to make these live classes interactive. This means that while I'm going to be explaining some things, showing some things, and teaching some concepts, I want you to not just be there listening or watching to what I am doing or saying, but to be also participate. So to also participate in the class. I mean to reproduce what I am doing. I'm going to share with you the project, so you are going to be able from anywhere in the world. You just need a laptop and an internet connection. You are going to be able to reproduce everything I'm going to be doing. You are going to see it right now with the project I'm going to share with you. So yeah, let's not lose any more time and let's go for it. Then let's start for the first thing, which is to get a drink here of my magic potion, as always. There we go. Then let me right now switch to my computer screen. It's not this one. This is my YouTube live stream. Okay, so here we are. Then we are going to be working in the construct application. Probably most of you already know it. For the new ones, this is the application that we are going to be working on. So you just need to create here a new account. You can come here to the page, theconstructsim.com, and then you can click on login in case you already have an account. In case you don't have an account, you can just create one now. It's free and it's going to take you just a few seconds, so go for it. Then once you log in, you are going to be in this platform, which mainly we can divide it into two parts. The first one is the Academy, as you can see here at the top, the Robot Ignite Academy, and the second one is the ROS Development Studio. Okay, then in the Robot Ignite Academy, basically you are going to find many different courses related to ROS, related to robotics. You can see here, for instance, robot dynamics and control, kinematics of mobile robots, arm kinematics, Kalman filters, etc. You can find also many courses about ROS, basic ROS, more advanced ROS, manipulation, ROS navigation, whatever. So you can have a look here at the Academy. Yeah, and in case you find any course that it looks interesting for you, just go for it. Then for this live class, we are going to focus more on the ROS Development Studio. So here you are going to find a section with public projects and my projects, okay? Then in case you have already been working here, you are going to already have some ROSjects here in your My ROSject section. Maybe you have previous live classes, I don't know. In my case, what I'm going to share with you today is this one. This ROSject, which is for the ROS Developers Live Class number 114, Reinforcement Learning for Robotics, okay? Then I'm going to share this ROSject with you, super easy, just by clicking here on the share button. Then I'm going to copy this link here, and I'm going to paste it right now in the chat. Let me come here to the chat and paste it. There we go. Okay, then once you click, you can click on this link directly, you can copy it and paste it here into the URL, whatever you want. In any case, once you get this link, you are going to receive here in your My ROSjects section, you're going to receive this ROSject. So you are going to get a copy of this ROSject in your workspace, okay? Then basically this is this ROSject, for the ones who don't know it, is basically a full ROS project which contains everything you need in order to develop a ROS project, which means you're going to be able to launch shells here, you're going to see it right now, an IDE. I have already placed it there inside this ROSject, a notebook with some documentation, also some files in order to start a gazebo simulation, etc. In any case, let me just show it because it's going to be easier to understand. So in order to start this ROSject, all you have to do is to click here in the Run button. Yeah, so let me click it here right now. And this is going to start loading, as you can see here, the environment. So automatically, here I'm going to get a Jupyter notebook loaded, which is going to contain all the theory, let's say, indications, instructions in order to follow today's live class are going to be self-contained inside this Jupyter notebook, which is the one we are going to be following today. Also, as you can see here, we have all the tools that we are going to be using. So we can launch here web shells, as you can see, as many as you want. These are just regular Linux shells. We are going to have as well an code editor, which I'm going to open it right now, by the way. Here I go, which is going to allow me basically to create, remove, edit, basically to manage my files in a graphical way, which is going to be always easier to do. Then in my case here, my notebook has not opened it automatically for some reason, so I'm just going to click here, and this is going to open the notebook for me. It's going to open it in a new shell, so I'm going to see it pretty big here. And yeah, that's it. So here I have my notebook for today's live class, as you can see. Then, yes, so the next step is going to be to start the simulation. In any case, I want to have a look at the chat to see how you are doing, if you are following me, if you are lost. Let me see here. So have you been able to get this ROSject into your workspace? Have you been able to launch it? Are you seeing already the notebook? What is the current status? Perfect, says Carlos Miranda. Okay, I don't like this because let me move this out. Okay, this is better. Let me see. Yeah, because I whenever I was checking the chat and everything, you were seeing it, and I don't think that looks very well. So I prefer to move this YouTube browser to another place so that it doesn't disturb you guys. Okay, so I can see now that you're perfect. Everything is crystal clear. Loading in progress. All good so far. Slow internet. It's not loaded yet. Okay, let's have some patience in this case. Notebook loaded and ready. Got it. Everything is working fine. Excellent, excellent, amazing. So everything is going smooth today. I love it. Then, okay, so as I was saying, the next step, once we have the ROSject loaded and we have the notebook also here open it, is to, well, first of all, let me just show you here a couple of requirements. So in order to follow this live class, and most of the live classes we do, basically, I would say that we have a couple of requirements. One, of course, is the to have a basic knowledge of Linux systems, how they work, basic Linux commands, etc. So this is a requirement for being able to follow this live class. Then we have here in our academy, as I showed you before, we have some courses on this, which are free in this case. For instance, we have you have here a course for Linux for Robotics, which is completely free. So you can start it right now and finish it and complete it in case you want to refresh your Linux knowledge or improve it. And also, in this case here, we are pointing to the C++ basics, but in this case, it's not C++. We have a course here about C++ for Robotics, which is free, but in this case, it's going to be more helpful, the Python one. So we have basically also this Python 3 for Robotics, as you can see here, which basically in this case it's the one that we are going to be using because we are going to be working with Python, all right? So we have also a Python 3 for Robotics course, which is also completely free. So feel free to click here in Start Course and check them, follow them, whatever you want, okay? Then once I have done this introduction, let me go back to my notebook here. Then the next step right now is going to be to launch the simulation. So we are going to be working with a gazebo simulation, okay? So in order to start the gazebo simulation, you have the steps here described in the notebook, which I'm going to do right now, and you should do them as well, okay? So what I'm going to do basically here is to just copy this command I have here, the first one, this export of the gazebo model path. So I'm going to copy it, Control-C from the notebook, and I'm going to paste it here directly to the shell. And now I'm going to do the same thing with the second command. So this first command, basically, as you can see, I am exporting here this gazebo model path environment variable. So basically here what I am setting is this environment variable so that the gazebo simulator is able to find the models I'm going to be using in this simulation. Okay, so basically it's only that, a visualization purpose. Then once I have set up properly the gazebo model path, I'm going to actually start the simulation, which is done with this ROS launch command. So I'm going to copy this ROS launch command and run it here in the shell. And this is going to start executing or running my simulation. Yeah, so now here I have it running, but in order to visualize the gazebo simulation, actually I'm going to click here on this cube icon I have here. So directly here in this cube icon, let me click it, and this is going to automatically open the gazebo window, yeah? So here, I'm going to be able to visualize the simulation I'm going to be working on today, yeah? So here, as you can see, we have a gazebo, we have a gazebo simulator, and inside we have a Turtlebot 2 robot here with some furniture here, let's say some circles that I have placed it here into the world that we will see in a moment what is its purpose. Okay, so summarizing. So the status we should all be right now is we have the ROS loaded, as you can see here. We have the notebook here opened and prepared to start following it, and we have the gazebo simulation loaded here as well, with the Turtlebot robot, with all these colorful circles here. So I want all of you to be in the same point as I am so that we can keep moving on together. So let me know in the chat if everything is fine, you are properly set up. I can see also some comments here. Let me see here. Recommended browsers are Chrome and Firefox. Yeah, that's right. So in my case, I am working here in a Chrome browser. So everything is going well, no issues. Everything is going smooth. It's loading fast. So in Chrome, everything should work fine, and also in Firefox, it should work fine. And actually in other browsers it should work also okay, but maybe there are some strange bugs in some rare browsers. So the recommended ones, as my colleagues are saying, are Chrome and Firefox. The recording will be available later, asked Juan Alberola. Yes, it's going to be available later, Juan Alberola. Says preparing project files. Still loading in Chrome, ready. Turtlebot loaded. I cannot see the circles in my gazebo window when I run the command. I cannot see the circles. Says Maxa. Okay, two options here, Maxa. So if you are not seeing these circles, you can try to click here on the reload button. Maybe this is going to help. Otherwise, if you are not seeing them, it's probably because you have not executed this export command. Yes, so it's important to first run in the shell this export command, this export gazebo model path, and later, once you have executed this first command, then you run the ROS launch command. Yeah, because this first command is going to allow you to, it's going to allow basically Gazebo, the simulator, to find all these models, which basically in this case are these circles here. Yeah, so if you don't run this first command, Gazebo is not going to be able to find these circles, so you are not going to be able to see them. Okay, so check, all of you, make sure that you execute this export command. And in case any other thing happens, you can try always to click on the reload button, which is basically going to reload everything. And maybe it's just a renderization problem, which is going to get solved by reloading. Let me see here. So I want to, sorry for the ones you are already set up, but since we are many people today, I want to make sure that almost everybody, the great majority, is set up and is not having any issues. Also, I can see that some people is having problems with loading times, so let's try to give them a couple of minutes to try and see if they catch up. Still loading here in Canada, says Cameron. I will come back to see the recording, says Vortex. Okay, that's fair. I can see George here is already helping other people. He's suggesting that maybe you have forgot to export the gazebo thing. That's a very good suggestion. Yay, it's working now, says Camrad, which was the one of the people, I think, that he was still loading. Loaded, working now. Okay, so it seems like people is starting to get their ROSjects loaded. Yeah, so today we are having a lot of people, so maybe this is causing some loading problems. Yay, finally works, says Bayana. Also, okay, that's great, that's great. Started to work. Okay, so we are starting to catch up, everybody. Okay, great. So yeah, very quick summary, and we will start with the class. So remember, once your project are loaded, just remember, come here to the notebook, open the notebook, and you just have to come here to the how to launch the simulation section and just follow the instructions. So basically you have two very simple commands. So we are going to open a shell here, a new shell, and we are going to run first, very important, this export command. You can directly copy and paste it from the notebook to the shell. That's perfectly fine. In fact, it's better to just copy it and paste it, because this way you are not going to introduce any errors if you try to write the command manually. So very important. First, we execute in the shell this export command, and then we execute the ROS launch command, which is the one that actually it's going to start the simulation. Then once we have the simulation running here in the shell, we can click on this cube here that we have in the bottom menu. We can click on this cube here, and this is going to open as you can see here, this gazebo window, where we are going to be able to visualize the gazebo simulation. And if everything is fine, you should see something like this, with the turtlebot here in the red circle, and all these other blue spots with a black one here at the end. So this is the world, the environment that we are going to be working today with. Yep. All right, so okay, so I think we can actually now we can start with the class, because I can say that most of the people is already set up. Alessandro says amazing. Okay, so I can see here Jay is making a very good question. He's asking, will this project be in my account indefinitely? Yes, Jay Shash, this project is going to be in your account indefinitely. So you can keep working on it after the live class. You can reopen it tomorrow if you want and keep working on it. So yes, it's going to be in your account indefinitely, so that you can revisit it anytime you want. Yeah? All right, so let's go for it. Then, today's live class. So we are going to be talking about the dynamic programming problem. Okay? Then, what is this dynamic programming problem? So basically, in this case, we are going to use it for reinforcement learning. So basically, this dynamic programming problem, besides a very scary, maybe and complex name, basically it's a way of optimizing programs, optimizing algorithms. Yes, so as we can see here, so dynamic programming is also known as dynamic optimization. So it can be exemplified basically as a method for solving complex problems by breaking these complex problems into smaller sub-problems. Yes, so basically the approach is that we are going to attack a quite complex problem, and we are going to divide it into sub-problems. Then we are going to solve these sub-problems, which are easier to solve, of course, than the big complex problems. And the important thing is that we are going to store, we are going to save these solutions for these sub-problems. We are going to save it, let's say, into a memory. Yes, and why are we saving the solutions for these sub-problems? Because we are going to reuse these solutions. Yeah, so let's imagine a very big problem, which we can divide it into sub-problems. Then probably there is a chance that some of these sub-problems are equal to each other. Yes, then it makes no sense if we solve the same problems 2 times. Yes, that's not efficient at all. If in our program or in our algorithm we are solving the same problem more than 1 time, we're losing a lot of efficiency. Yeah. So in dynamic programming, what we do is to, once we have divided this big problem into smaller sub-problems, and we solve these sub-problems, we are going to save the solution for these sub-problems into memory, so that in case we find this sub-problem another time, we already have the solution stored into our memory, so we can use it and we don't have to solve again the problem and lose time and lose resources on doing that. Yeah, makes sense? So first thing is that in order to apply this dynamic programming concept, we need to have a problem which first can be divided into sub-problems, and second, we know that these sub-problems are going to be repeated. Yeah, so we are going to find the same sub-problem more than once. Yeah, so this is, we need to have this scenario in order to be able to use dynamic programming. Yes, because it makes no sense that we keep storing solutions for a problem if we are not going to need it anymore. It makes no sense. We are losing, we are wasting memory. Yeah. So dynamic programming has to be used or has to be applied in a scenario where we know that we are going to have to solve the same problem more than one time. Yeah, makes sense? Then in this case, programming, this dynamic programming concept is going to allow us to optimize a lot our algorithms, which, for instance, in reinforcement learning and artificial intelligence is going to allow us to optimize a lot our training times, for instance. Yeah. Let me get some drink because I'm talking a lot and I'm starting to get my throat very dry. All right. I can see here. Started to work, loaded finally, loaded, can see the circles on the turtlebot, it is working just fine. I am all set now, thanks. Alessandro says, amazing. Okay, I love your enthusiasm, Alessandro. I also think this is amazing. Voice level is a bit low, is suggesting Ibrahim. Okay, I'm going to try to get a bit closer to the microphone. You are welcome, Cameron. You are very welcome. Okay, so let's keep going. Then we have done this this introduction to dynamic programming, so more or less what it is. Then one of the basic things, one of the basic problems that we can apply this dynamic programming to is the minimum cost problem. Okay, then let us imagine a scenario where a robot has to travel from a point A to a point B. Then this robot is going to move in a maze without obstacles. Then our goal is going to be to write a function which returns the less expensive path to reach the destination cell. So we don't have to imagine much here because we can check directly to our simulation. So let's imagine that we want to move our robot from its initial position, which is this red circle, into a goal destination, which is this black circle that we have here. Yes? And in order to reach this, we are going to need to move through these blue circles that we have here in the way. Yes, we can think of these blue circles as a kind of maze. Then each one of these blue circles is going to have a cost. Okay, this cost in this case it's not depending on the distance. So this, as you can see, this circle is farther away. So this one it's closer to the robot than this one. Yes, but this in this case it's not going to mean that this circle has a higher cost than this one. Yeah, in this case, the costs are not going to be related to the distance. So we are going to just apply some costs to each circle, which are going to be arbitrary. Okay, we are going to be able to change it, to change them later, etc. Then let's imagine this. Yeah, so we need to find out the best path, which means the minimum cost path from the red node. Let's start talking with some more meaningful terms. So let's talk about these circles, which I was calling them until now. Let's change and start naming them nodes. Okay, so these circles are going to be nodes. Then, in order to make the robot reach the goal node, which is this black node that we have here, we are going to pass through all these intermediate blue nodes. Then, as I just said, each of these nodes is going to have a cost applied to it. So if I go through this node that I have here at the left, let's say that it's going to cost the robot 5 units. If I go through this node I have in the right, it's going to cost the robot 7 units, let's say. And if I go through this node that I have here in the middle, it's going to cost the robot 1 unit. Then, which should be the node to go? Which one would you choose? Remember, this one has a cost of 5, this one has a cost of 1, and this one has a cost of 6. So which one would be the one to go? I know it's a very silly question, but can somebody answer that? Middle, okay. So Biana is saying middle. Yes, you're right. Let me read here the chat. I can see some... I waited for 7 minutes and... Sorry, the icon is the third, starting from the left. Go to the icons on the bottom left and click on the third icon starting from the left. This should open the notebook. Yeah, so let me just show this very quickly. So here we have all the tools that you are going to be able to use here in the ROS Development Studio. The first one here at the left is the shell. So you can, in my case here, I have opened it, I have launched here my simulation, but I can minimize this one and launch a new one. So here you are going to be able to launch as many shells as you want. Then this one is the code editor, which basically is this one, and here is where you are going able to manage all the files in a graphical way. Yeah, so here I have some files prepared, which we are going to see in a moment. You are going to be able to open these files, check the code we have in them, modify them. You can create new files, etc. So just a code editor, a graphical code editor, yeah? Then the third one here is the Jupyter Notebook. Here is going to show you the notebooks that you have here. In our case, we have this one, which is the notebook for today's live class. You can create new notebooks in case you want. You can create a new notebook and put here your notes, whatever. Yes, this is basically a Jupyter Notebook interface. The fourth one here is the gazebo simulator. So this is going to open the gazebo window so that you can visualize the gazebo simulation. And the final one is just graphical tools, which you are going to be able to visualize some graphical applications. For instance, if you have worked with ROS, if we launch an RVs session here, you are going to be able here to visualize RVs. Okay, so this is the graphical tools for. In this case, we are not going to be using RVs, so we don't need it. But basically, that's it. Yeah, so these are all the tools that you have here. I mean, a very quick summary. The middle one, okay, I can see that everybody is starting to answer here. Lowest cost, middle one. Center, the middle one. Ahmed is saying that the notebook list is empty, okay. That makes no sense. So you have to find this one here, the default EPI notebook. Yes. If you are not seeing nothing here, try to refresh here, click on the reload button, and you should either have the ROSject automatically open it, or if not, you should have this default EPI notebook, which you can click here, and it's going to open this notebook for you, okay? Then, all right, so I can see that many people has already answered the middle one. Yeah, that's right. So in this case, the one which has the minimum cost is the middle one, so we should go for the middle one, okay? And then the same repeats for the next row of nodes, yes? So this one is going to have a certain cost, this one another cost, and this one another cost. Then we should keep moving through the one which has the lowest cost. And the same, we are going to repeat this process until we reach the last one, the black node, which is our goal. Yeah, makes sense? Then basically, this is the summary of the minimum cost problem. So here we can define a maze cost matrix, etc. I'm going to escape this, so you can check the code here. But basically, it's the idea is this one. So I think you get it, okay? In this case, just let me make a specification here. Is that in our case, the agent that we are going to train is going to be able only to perform 3 movements, which are up, down, or diagonal. Okay, so we are going to be able only to move up. Yes, up means, let's say, from this node to this one, down means from this node to this one, and in diagonal means from this node to this one, okay? In this case, this is the agent. So yeah, so then let's keep moving and go for the next section, which is the recursive computation versus dynamic computation. Okay, so basically these are this is something pretty interesting here, because basically these are two ways of solving a problem, which are going to show us basically the main point of applying dynamic programming, which is this optimization. Yes, so we are going to see an example, which is basically to calculate a Fibonacci sequence number. Yes, then we are going to do this by creating a program which uses recursive computation, and then we are going to solve the same problem creating a program which uses dynamic computation. Okay, then we are going to compare these two algorithms and see which one works the best. So first of all, we are going to come here to the CAD-King workspace, and we are going to we are going to come here to the IDE, which I have here. We are going to open, in this case, the CAD-King workspace. We are going to go to the SRC folder. Let me make this a bit bigger so that you see what I am doing here. Okay, so I have opened here the IDE, then I have opened the CAD-King workspace, and I have opened the SRC folder. Then inside here, you are going to see that you already have a Python file which is named optimal path ros.py. Okay, for now, just forget about this file. We are going to check it in a moment. And here, I'm going to create here inside the SRC folder a new file which I'm going to name Fibonacci1.py. Okay, then inside this Python script that I have just created, I'm going to copy this code directly from the notebook, and I'm going to paste it here into the script I have just created. Okay, then as you can see, this is a very simple Python code, which basically it's going to solve the Fibonacci sequence for a certain number. In this case, we are calculating it. We are calculating the Fibonacci number for 35. Okay. Then basically here we have created a function which, in case the Fibonacci number is 1 or 2, it's going to return 1, and in case it's higher than 2, it's going to return the Fibonacci number, the previous Fibonacci number plus the previous Fibonacci number. So for instance, computing the Fibonacci number 35 is going to return us the Fibonacci number 34 plus the Fibonacci number 33. Yes? So basically it's going to start from the top, and it's going to go all down, calculating all the sequences until it has calculated all the Fibonacci numbers, and then it's going to start summing them until I get the final number, which is going to be this, the sum of the Fibonacci number 34 plus the Fibonacci number 33. Yes, but as you can see, I'm calling here each time the same function. Yes, so I'm going to be recursively, as you can see here, this is the recursive method. I'm going to be recursively calling one time and another this function in order to solve the Fibonacci number. Yeah. So this is the recursive method. Then let's just execute it right now. Let's open a new shell here, and we're going to move to the CAD-King workspace SRC folder directory, and here I'm going to directly execute this Fibonacci1.py script I have just created by running the command python and then Fibonacci1.py. Okay, then I'm going to run this, and this is going to compute the Fibonacci number for 35 in this case, which is this number that we have here. Yes. Then the thing here is that we can not only execute it like this, but if we add here the time keyword at the beginning, we are going to be able to get some data of how computation time it takes to solve this program in specific, this one. Yes? Then let me run one more time the program with this time keyword at the beginning. And basically here I can see that it's taken in total 2 seconds, 2.9 seconds. So basically almost 3 seconds. Yes? So it has taken almost 3 seconds in order to solve this program, this simple program. Why? Because I am calling one time and another the same function, and I am calculating multiple times. In this case, I'm calculating the same problem. Yes. So here we have here if we go down here, you're going to see how we are solving this. So let's imagine that we want to solve the Fibonacci sequence for the number 5. Then we are going to get the number n minus 1 and n minus 2. Yes. So we are going to need to solve these two sequences. Yes. Remember, for solving the Fibonacci sequence for a certain number, we solve the Fibonacci sequence for the number n minus 1 and then n minus 2. So if we want to solve it for the number 5, we are going to solve first the Fibonacci sequence for the number 4 and the Fibonacci sequence for the number 3, and then we are going to sum these two sequences. Yes? Then what I am doing in this program is basically this. So I'm solving this sequence, I'm solving this sequence, and then I'm solving again the sequence for the n minus 1 and n minus 2, and again the sequence for the number n minus 1 and n minus 2. But as you can see, for instance, here I am solving the sequence for the number 2, and here I am also solving the sequence one more time for the number 2. Yeah? Then here I am solving the sequence for the number 3, for instance. And here I am one more time solving the sequence for the number 3. So can you see the idea here? So basically I'm solving the same problem many times, which is not efficient at all. Yeah? And basically this is making my program take 3 seconds to solve this. Yes? So what if we create a script which uses this dynamic programming or dynamic computation approach? Yes? Then this is what basically we are going to do in this script. Then I'm going to create another one, which is going to be Fibonacci2. Fibonacci2.py. Then in this Fibonacci2.py script, I'm going to copy here the code. Sorry. I'm going to copy here the code, and I'm going to paste it into my Fibonacci2.py script. Okay? Then let me right now just run it. Fibonacci2.py, Python, Fibonacci2.py. And I can see that I have directly, without checking any data, I can see that the program has been much faster than the previous one. But let me verify this by using the time function here. So time Fibonacci2. There we go. Okay, so I can see now, I can compare here the two programs. Fibonacci 1, which uses the recursive method, has taken 3 seconds in order to compute the number, in order to run the whole program and compute the number. While the Fibonacci 2 Python script has taken basically 0.017 seconds. Yes? So 1 millisecond, basically. Yes? So it has taken 1 millisecond to solve the problem, which is much, much lower, as you can see. Yes? The result is the same. So basically, in order to get the same result, I have reduced the time drastically by just using the dynamic programming, approach. And what is this dynamic programming approach? Well, basically, as we have talked before, what we are doing in this program, you can see basically here that we are using this fib memo function, which basically is going to store. Here is where we are going to store the results that we already get while calculating all the Fibonacci sequences. Yes, so here we can see the difference in a diagram, which is much more clear. So let's compare this to the previous example that we have seen. Let's imagine that we want to solve the Fibonacci number 5. Yes, and we have then again to compute the Fibonacci number n-1, which is 4, and n-2, which is 3. Then once I solve the this Fibonacci, the Fibonacci sequence for the number 3 and the number 2, I'm going to store the solutions for these sequences into our memory, as you can see. So here I am storing the sequence for the number 2, and here I am storing the sequence for the number 3. Yes? Then when I go back here and I try to compute again, I need to compute again this Fibonacci sequence for the number 3. Instead of computing everything again and keep going down, I can directly come here and take the value. Sorry, this has disappeared. Okay, I have double clicked it. Yeah, so instead of keep going and computing the sequence again and keep going, I can directly take the solution which I have already calculated and stored in my memory. And the same goes for the Fibonacci sequence number 2 in this case, which I need here. Instead of computing it, I can directly get the result which I have stored here in my memory. Yes? So as you can see here, basically, I am checking if I have I have any value in the memory, and if I have a value in the memory, I'm going to get this memory. Yes, so if I already have that sequence calculated and I have stored it into my memo, I'm going to return this value. I'm not going to keep going and I'm not going to keep calculating. I'm just directly going to return this value I have in memory. So this is going to optimize a lot my program by not having to compute the same problems, by not having to solve the same problems one time and another. Yeah? Makes sense? Okay, then we are going to apply all this right now to a practical example using ROS. Yeah, so we are going to be using actually now our robot in the gazebo simulation. So we are going to apply all this into creating a program which makes my robot move through all these nodes until this gold node, which is the black one, and I'm going to compute the minimum cost path through all these nodes until I reach the goal. Yes? Then, for this, let me come back here to the notebook. We have you have here a scheme of our situation. So the node A is the red one, basically here. These nodes here in green are the blue ones we have in the simulation, and this black one is the node J we have here. Yes? So here we have so basically we are going to compute this as I have explained it before. Yes? So we are going you can see here all the process. Yes, so we have the cost of going from the node H to the node J here defined in the FH function, which is basically 3, as you can see here in the number. Yes, so here in all the nodes you have all the costs from going from one node to another. Yes, so going from the node A to the node B is going to cost 2 units. Going from the node 8 to the node C is going to cost 4 units, etc., etc., etc. Then FH, which we have here in the first line, going from the node H to the node J is costing 3 units, and going from the node I to the node J is going to cost 4 units. Yeah, so we are going to start solving from this, and then we are going to keep going until the start. Then, and so on. Yeah, so for the node A, then we have here FA. We can compute and look for the minimum between FH plus 1, which FH in this case it's 3, plus 1, it's 4. So the total cost of going from A to J going through the node H is going to cost me 4 units. If I want to go from the node E to the node J through the I node, it's going to cost me 4 units plus 4 units, which is a total of 8. Then the minimum between these two, of course, it's 4. So in this case, the minimum cost path is going from A through H through J. Okay, and so on, so on. Yes, this way we can compute all the cost, and at the end, the path that we are going to get is this one: A to C to E to H to J. Okay, then we have here a Python program which basically computes all this, which is named optimal path. Then we can basically create a new file here as well. Let me go one more time here to the IDE, and I'm going to create this optimal path.py Python script. Okay, then I'm going to copy the code from here. Oops. Let me copy it from here. I'm going to paste it directly here, and I can run it directly here, Python optimal path. Oops, I don't know. I have touched something here. Control C, Control V, there we go. Okay, Python optimal path.py. And as you can see here, it returns me, after running this program, it returns me the optimal path for the robot is A, C, E, H, J, which basically it's the path that we have here. Yeah, so basically, let's have a quick look at this script. We have defined here in this matrix all the costs from node J to node A. We have here in this matrix defined all the costs. This is basically the same as we have here in a graphical way. Yes, but we have placed all these costs, in this case, into this matrix. Yeah. Then we are computing here the fx function, which is this function here. We are doing all this computation using dynamic programming. So as you can see here, we are using the this memory. Yeah, so we are storing the intermediate results into memory. So we don't need to compute them again. Yes, so we are using the dynamic programming approach in this case here, in order to compute the less minimum path. Yes, in this optimal node function, we are finding the next node and returning. Yeah, so yeah, all this here in the compute and in the optimal node here we are searching from node to node, and here we are computing everything. And at the end here we are returning the full optimal path in this optimal path draw function, and we have here just the main function. Okay, so yeah, here we are basically appending everything to this optimal path array. We are appending all the nodes, which are going to, at the end, draw the optimal path, okay? So, yeah, so here we are getting the solution by using this dynamic programming, which we can see printed here. But in any case, we are still not moving the robot, right? So once we have found the optimal path here, using dynamic programming, we can apply it to ROS in order to move the robot. So this is basically what I have done here in the optimal path ROS. So if you open this script that you have already here, optimal path ROS, basically what we are doing is the same. Yeah, so we are defining here all the costs. We have the same functions. Here we have a different, here we have an alternative. So this is the costs that I have defined here in this graph. But you can modify these costs if you want. So in fact, I encourage you to do it. Because if you modify the costs here, obviously the optimal path is going to change. Yes, if you play with all these costs of going from one node to another, obviously the optimal path is going to change. It's not going to be this one anymore. So I highly encourage you to try this, to try with different costs and see how this affects the path. Okay? Then You can see here all the functions. We have the same functions as in the optimal path script. We have the compute function, optimal node, and optimal path row. But I have added here all the functions in order to move the robot. Yes, in order to send commands to the robot through waypoints and publishing into the command bell. Topic, reading from the odometry, etc., etc., etc. Yeah, so I'm not going to go into all these functions right now. This is more a ROS basic thing. So in case you want to learn how all this works, you can have a check out our courses, ROS Basics course, for instance, to see what it's going on over here. But basically, what I am doing here is to, once I have computed the optimal path, which is this sequence of nodes, A, C, A, H, J, I am setting for each of these nodes a waypoint here, and I am sending instructions to my robot to go to the next waypoint. Yes? So basically, if I run this new program, you're going to see that the robot is going to start moving to the next node, which in this case it's the middle one, as we can see here, is going to the C node. Now it should go to the left one, which is the E node. Here we see it already turning, and it's going to head towards this E node here. You can see the robot, it's already going there. And now it should keep going through the optimal path, following through the H node, and finally reaching the J node, which is the goal one. Yeah, so let's see how it keeps moving. We can see it there. And finally, it's going to reach the black node, which is the goal. Yeah? There we see it. All right, so of course, this path, this minimum cost path that I have computed and executed here, it's using this costs matrix. Yes, if I change the values here, for instance, here you have an example, another costs. So if you change the costs of going from one node to another, you are going to obviously make all this computation change, and you are going to make the optimal path change. Yeah. So I really encourage you to do so, to play here with the values. Also, of course, you can check here all the functions more in depth. You can play with it after this live class, so that so yeah, this is why we share the ROS with you guys, so that you are able to practice here, and this is the way that we think that you are going to be able to learn more and to get the most of these live classes. Yeah. So yeah, basically we have already reached the hour. So let me go very fast here. Nice, says Engineering Nation. How is the cost matrix setups? Okay, I see he has removed already the command, but basically yes, it's done here. So we start with the oops, where I have my program. Yeah, so we start with node J, which has no cost, of course. Then the node I and node H have only one cost, which is 4 and 3. Yes, these two only have one cost, which is 4 and 3. Then node E has two costs already, which is 1 and 4. So we have defined it. Yeah, here it is. I wasn't finding it. 1 and 4. For instance, the node G has 3 and 3. We have defined them here. Yes, so this is basically how we are defining all the costs in the matrix. Okay, so that's it. That's how do the rows correspond to the nodes? It's done like this, George. You can see it here. Yes. So it starts from the left which would be the node J considered, which has cost 0, and then we start with the cost of the node of the Y node and H node, which are 4 and 3 respectively, as you can see. Then, for instance, the node E, which is here, we are setting the costs 4 and 1, which are the costs of going from the node E to the nodes I and H. Yes, then for the node D, for instance, which has the node D, we have it here, it has 3 costs from going for the going through the node E or F or G, which are 4, 1, and 5. Then we define them here. Yes? And finally, the last one, which is the node A, we define them here, 2, 4, and 3. 2, 4, and 3. Yeah? JSHAS is it correct to say that the path computation from A to J is recursive, but the computation from J to A is dynamic programming, since we already have the suboptimal path from J to A particular node in the middle. That's right, Jay. That's right. That's totally right. Yes, it's correct to say that. Yeah. What is the subcalculation that is being done? I don't get your question here, Kumar. I don't know very well what you are asking here. The subcalculation, I don't know what you mean here by subcalculation. Sorry. Okay, in any case, guys, if you have more questions, please leave them here in the chat of the video. So as I have said, we are going to upload a video of this session once it finishes, which is now. So you can leave there your questions. You can go to our forum if you want also. You can come here to... let me come here. So you can come here to our forum by clicking here in the arrow icon, here in the yellow arrow icon, in the yellow question mark icon here. You can click here and this is going to take you to our forum where you can ask if in case you have any doubts about the live class or about the courses or whatever. Okay, so in case you have any questions, I encourage you to do this. So yeah, we are going to leave it here for now. Let me change here to my camera again. Thank you very much. Thank you very much for being with me here during this hour on this live class. I hope you enjoyed it. I hope you have learned something from it. You have grasped some new knowledge, even if it's something small. That's enough for me. But or at least that you have had a good time. So thank you very much for being here with me. I will see you next Tuesday with next live class. And until then, just as I'm saying always, take care and keep pushing your ROS learning. So thank you very much and bye-bye. See you soon.
What are you doing, Alberto?
I'm training this intern with ROS.
Oof. Did you have the same experience? Spending too much time equipping your team with ROS skills? Check out our ROS Online training solution for enterprises. A fast and easy way to empower your team with ROS. From ROS basics to manipulation, perception, AI, ROS2, everything your team needs to learn is here. Practice with real and simulated robots. Train your team by doing from day one. Also, our ROS experts will provide you 1 hour of consulting services to boost your robotics projects. Want to become a happy Alberto? Request a demo today.